So we ran out of power there and we're back on. When considering these two structures, again, we've drawn two different chair forms of the same exact molecule. It's got three different substituents on it. We've seen that this one would be the more stable form. What we want to do now is draw a planar cyclohexane representation with the correct assignment of three-dimensional geometry, so dashes and wedges. What we're actually going to draw is the correct stereoisomer for this exact orientation. And so we start off with a planar cyclohexane. Where exactly you put the first group doesn't matter because all these carbons are the same. I'm just going to choose to define this carbon right here as the one that bears the methyl group. And so if we look at this methyl group, that methyl group is going upwards, and to me that's equivalent to coming out at us, upwards or out. And so when I define this methyl group as coming out at us, now I can reference the rest of the groups to that position. Well, the methyl group is going straight upwards. The fluoro that's bonded to the carbon next to it is not going straight upwards, but it's going slightly upwards, still in an upwards direction. And since they're both going upwards, we represent that with a wedge as well. Now when you look two more carbons down the line, opposite from the methyl group, the hydroxy group is going directly downwards. So that would be a trans relationship to the methyl group or to the fluorine. And so we represent that with a dash. Now if we've done this correctly, this drawing should also represent what is observed here. And it certainly does. The methyl group and the fluoro are cis to one another, still oriented in the same general direction. And the OH group, still angled downwards from the carbon, is trans to both of those groups. So these two groups are cis to one another, and these two groups are trans to one another. The last thing you should do is then try to draw the structure with the planar cyclohexane representation. Draw the structure that would give you the most stable stereoisomer, or the isomer where all three groups could be equatorial. And so to do that, usually you have to start with a chair conformation. Well, how can we draw a chair conformation where all three groups are equatorial? Well, this one's pretty close. The only problem is that the fluorine is axial. So if we redraw a chair, we like the position of the OH group, equatorial. We like the position of the methyl group, equatorial. But we want to change this position. In changing that position, we are creating a new molecule, an isomer of this representation. So if this is axial going up, the equatorial position here would be going downward. Again, you might find it helpful to go ahead in and draw the axial positions. But certainly you don't have to. And these positions, again, are just occupied by a hydrogen. Now that we have this representation that must be the most stable representation, we can draw what it looks like in a planar structure. Again, the methyl group, since we didn't change it, oriented slightly upwards. I'm going to choose to define that as a wedge. Once I've defined that as a wedge, everything references this group. The fluorine now, instead of being cis to the methyl group as it was in this chair, notice it's angled downward from the carbon it's bonded to. The hydroxy is also angled downward from the carbon it was bonded to. And so this chair conformation would represent the most stable possibility. Now, the fluorine and the hydroxy group are cis to one another, and both of these groups would be considered trans to the methyl group. And that should give you some insight into how to draw more complicated cyclohexanes.